Hi, my name is Sam Daigle, and I'm going to be talking about DFT, covering the basics of how it works and how it might be used to help answer your research questions. Density functional theory is a quantum mechanical approach to matter, in which electron densities are used to calculate the behavior of atoms. DFT is commonly known for calculating binding energies and electronic band structures for many body systems at the ground state. All this means is that we're considering systems that have more than one electron, and they're at the system's lowest energy state, typically at 0K. In the 1960s, the approach was developed in which electrons are treated first as non-interacting and then modifying for the exchange correlation energy. The first three terms in the total energy equation, which represent the kinetic energy, the potential energy, and the Coulomb energy, can be solved explicitly, leaving only the exchange correlation term to be approximated. The many levels of approximation for the exchange correlation exist on the so-called Jacob's ladder of DFT, where you trade off increased computational expense in order to move up a rung to a more accurate approximation. The lower rungs begin at the local density approximation, or LDA, and the generalized gradient approximation, GGA, before moving up to the more accurate and more expensive hybrid functionals. To simulate a materials system using DFT, you must first specify the inputs to tell the program what parameters to use. Simulation inputs can be as simple or as complex as your research question requires. The minimum requirement to run a DFT simulation is a reasonable atomic structure input and the proper set of potentials, but some materials systems require careful tuning of some parameters in the calculations to obtain the correct result. In some cases, it can be important to choose a very accurate potential, while for some simple structure calculations, a simpler and less expensive approximation may be appropriate. When considering what parameters to use, we generally use a combination of fitting to experimental data, DFT or material-specific expert knowledge, and convergence. Parameter convergence requires iterative simulation of your system at increasingly precise and increasingly computationally expensive intervals until the desired precision is reached. Now let's look at some of the outputs that can come out of a DFT simulation. The most basic output for a DFT simulation are the atomic positions. This can tell you things like the lattice constant for a crystal, the equilibrium bond distance for a dimer, or even the radial distribution function for large cells of disordered systems. Perhaps the most common used outputs of DFT simulations are total energy calculations. Total ground state energies can be compared between different phases or compositions, and when combined with thermodynamic equations, can be used to establish equilibrium states for materials. In addition, experimental data from thermodynamic tables can be used to extrapolate certain DFT results to temperatures above 0K. It's important to note here that while DFT simulations can find the local minimum energy structure, it's necessary to have a reasonable approximation for the lowest energy structure as an input if the true ground state is what you're looking for. This can sometimes be used to a researcher's benefit in that you can compare the energies of different structures that may or may not exist in nature, or that may only exist under extreme conditions. Charge densities calculated by DFT can be used to characterize the bonding nature of a structure, and Bethe charges can be calculated to partition the charge density and ascribe total energies to each atom in the system. Finally, one of the more useful outputs of DFT is the ability to calculate band structures of materials. Through proper tuning of the input parameters, these calculations can be made very precise and, while often computationally expensive, they can provide insight into materials that can be very difficult to obtain from other methods. To summarize, DFT is a quantum mechanical approach to matter, in which electrons are treated as a density with an approximation applied by way of the exchange correlation functional. Through careful tuning of parameters, we can calculate outputs which provide insight into the mechanisms behind measurable properties. I hope this introduction gave you a basic understanding of how computational materials scientists approach problems using DFT and some of the ways it can help solve your research problems. In the second module, we will go through a few examples of applications of these methods.